space up there in the next to step 3 there's that blank space, because I want you to, if you need to, use that space to draw a curve. Because Aaron, I don't want to lose this idea of a one-sided interval. I love that idea, but I want to visualize it. Your TI will draw it for us too, but I like the idea of actually sketching it with more context. So this is always, I tend to always draw a curve in that space off to the right. Now, I know there's a bell curve. I know there's a bell curve because the central limit theorem guarantees it to me. And I know that in the general population, 12% of people get sick. Make sense? That's what we know from historical fact. Now, what we're going to do is we're going to normalize this, just like we did in 243. In 243, we analyzed at least a half a dozen data sets at the end of 243. We analyzed IQ, we analyzed human pregnancy, we analyzed flight seats, if I remember correctly, in jet widths of flight seats. That was on your exam, if I remember correctly. We analyzed the Tower of Terror, how tall you have to be on the Tower of Terror. We analyzed, what else did we analyze? I'm losing track now. There's a whole bunch of different data sets. The way you analyze all those data sets is you make them all collapse down onto one very special bell curve called the standard normal. That's why I gave you guys a program called STANormal back in the day. If you had me in 243, you had this. Every single situation you have represents a different bell curve. The average heights of guys, the average heights of girls, the average weights of guys, the average weights of girls, the average lifespan of my camera stand, the average lifespan of my camera. All these things have a different bell curve attached to them. So it's kind of inconvenient to always be dealing with their individual curves. If you can transform them, though, down into a standard curve, that makes our lives much, much easier. It saves us having to carry around a huge book with infinite pages in it. We have one book with one page, the Z-curve. So that's what we're going to do. We're going to turn the raw data into normalized data. So we have to have a conversion. We have to have a conversion. Now we know that 12% goes with 0. That's just a given. You can always throw a 0 down in the middle of your curve, because that's where it's always going to normalize to an average of 0. If the z-scores go positive, that means you're above average. If they go negative, they're below average. The question is, and you guys have already asked it, is how far below average are we? We know that we came in at 10.1%, correct? We know, I'm going to arbitrarily put it there. I have no idea where it actually is yet. It could be here, it could be here, it could be anywhere. The question is, if that's 10.1%, what's the normalized value so that I can compare it to 0? I can compare 10.1 to 12. It's 1.9% lower. Is that significant? Don't answer that question. Don't answer that question. Shrug your shoulders. Nobody's shrugging. Shrug your shoulders. We don't know! How come we don't know? We don't know what the standard deviation is of the sampling distribution. 1.9% might be significant. It might be nothing. You have to know. I'm 3 inches taller than average. Is that impressive? Not if the standard deviation is 6 inches. That means I'm at 1/2 of one standard deviation above average. Woohoo! Right? But if the standard deviation is 1 inch, that means I'm 3 standard deviations above average. We need a ruler with a fixed scale on it to tell me how far down this is. Does that make sense? Now, we have the tool already. You learned it in 243. And we're going to keep using it in 244 over and over and over again. It was called a z-score. It was called a z-score. Average taken away from the data divided by the standard deviation gives you an idea of extremity. We're going to take that and create what's called a test statistic. And this idea of a test statistic is always the same. This test statistic is going to give us this value right here. Every time, from now till the end of week 10. We just have to convert it. We have to learn the conversion for each different case. And it's a piece of cake. They're all very logical. Here's how they all work. They all work the same. You take your sample average, sample statistic, whatever that may be. In this case, it's p hat. We'll come back to our numbers here in a second. We take off the assumed parameter value which we also know in this case, because we're making an assumption about the vaccine being useless. And then we divide by something, because right now, that's easy to do. It's 10.1 minus 12, duh, 1.9, negative 1.9. It's working, it's negative. But Elizabeth says no rule, because you only know if 1.9 is significant if you do what? You got to have a margin of error. So what you're going to do is you're going to divide by the standard error. And you have to calculate that for each individual statistic. Now don't be freaked out by this. It's not a bad calculation. It's actually pretty straightforward. But you have to know what that standard error is. Is it this? Is it this? Is it this? Is it this? I don't know. I mean, until you know what the margin is, you have no idea how big 1.9% is. It's all about a ruler you're putting down on the paper. If you look at a map and go, holy crap, I gotta drive to Boise. But yeah, it's only 5 inches. But yes, but every inch is 150 miles. Oh, that's different than every inch being 5 miles, right? That's the idea. How big is an inch? Let's find out. So now, this is the general idea of a test statistic. We're gonna live and breathe by that for the next 5 weeks of this class, because that's how we get the number to put on this curve right here. All we gotta do now, let's feed our numbers in. Let's feed our numbers in. Let's make it specific to our case. The test statistic in this case is going to be a z. That's why I had you in step 6 circle z, because I want you to know which to use. It's important to know. The sample statistic we got is p hat. You will know that automatically when you read your data. Not when you read your data. The assumed population parameter is little p, which you will also know because it will give itself to you in its data as well. Good so far? Fair? Maybe-ish, getting there. The standard error. This is the interesting part. This is always the interesting part. You've already calculated this before. You might remember, I'm going to scratch something over on this sideboard, just for you to refer back to. You might remember calculating a margin of error when we did proportion confidence intervals. Don't write this down. You've already written it down many, many, many weeks before. But your margin of error when you calculate a single proportion confidence interval was found by taking a z confidence multiplier and then multiplying by p hat times q hat over n. This right here is the standard error. When you multiply it by z, it becomes a margin of error, which is usually 2 standard errors. That's all we got to use now again. Except with one small adjustment, and here's why. I want to explain to you why the small adjustment occurs. Come back over to here. It's a big square root. You guys see this okay? I'm sorry about R2-D2 here. It's a big square root, but instead of p hat q hat over n, it's p times q over n. Reason being, you're building the curve around the known population value or the assumed population value, which is little p, not little p hat. Your population observes this proportion, which means the error around it has to observe this proportion as well. Does that make sense? So if you drew 1,000 people from the population that has that flu rate, this is the plus or minus around those 1,000 people. Is that believable? It might not make 100% sense right now, but is that believable? If you build the standard error around the sample, how do you have any idea if you're actually talking about your population correctly? You might not be, right? Only if your sample is exactly the same as your population. But do you ever know that? Unfortunately, no. You know your population from years and years and years of study, but you don't know your sample outside of your sample. You're trying to compare your sample to the population. So these pieces here have to be based on the population values. That's the cool sample value. Please, Brandon, go. Ask me this question.
So the P would be 0.12?
Yes, sir.
Okay.
0.12, 0.88.
And then the P hat would be the 0.101?
Yes, sir.
Okay.
So really, that's why I wish I had different colors. Let me add a little bit of purple to the green, make it stand out. That guy is the oddball. This and this are based in the population. That's based in the sample. Much like in 243 with the z-score. You had mu and you had sigma. Mu and sigma are based in your population. And then you had this x value that was your sample data that was compared to it. Same exact places as they were in 243. Great question, Brandon. Thanks, sir. Did everybody catch Brandon's question? Now, let's actually do this calculation, shall we? I think we should. Yes? Let's run the values through. Brandon's already actually given us most of it. For our particular case, so this is the general idea of a test statistic. This is the some more specific general test statistic for proportions. So for us to figure out what goes at that question mark, we have to then run